Oh, okay.
Okay, welcome back to the NCGNT seminar. So it's our pleasure to have Eduard Vilalta from Barcelona. So Eduard is going to talk about non-ware scatterness and the global Gleam problem. Okay, Eduard, take it away.
Great. So thank you very much for inviting me, not just to this seminar, but also to the institute. It's my first time visiting and I had a wonderful time. So thank you. So as I mentioned, my talk is going to be about nowhere scattered system algebras and the relation that they have with the global Gleam problem. And in some sense, as the name of the talk suggests, I'm going to be dividing the talk in two sections, which will be, in an hour. And the first section will be about this family of system algebras and explaining the sort of permanence properties and characterizations that they enjoy. And then the second section of the talk is going to be about truly the global Gleam problem and the global Gleam property. So first, to start with this first section. Oh, by the way, let me know if this is okay. Yeah, okay. So this first section, before even defining what nowhere scattered system algebras are, let me briefly recall what scatteredness means in both the topological setting and the system algebraic setting. Since informally, nowhere scattered system algebras are going to be those that are really far from being scattered. So mainly, and as all of you know, there are many ways of relating topological spaces and system algebras. And one of those ways is by considering a topological notion and producing a translation for it in the setting of system algebras. In other words, creating a system analog for that notion. And the idea behind this procedure is that usually you not only want to get a new definition for system algebras, but you also want to be able to translate some of the results and characterizations that you have here into this new setting. And this has been done successfully many, many times. For instance, open and closed subsets translate into wide fields and quotients, and covering dimension translates into a family of dimensionality notions of system algebras, like the nuclear dimension. And one of these translations that works really well is when one takes notion of scatterness in topology and produces its system algebraic translation, which is also known as scatterness. And the point, as I said, is that this notion, the notion of scatterness in topology, has been studied for many years and it's many characterizations and has very nice permanence properties. And you sort of hope that by doing this, you get a notion in system algebras that will also have nice properties and nice characterizations. This was done by Jensen in 1977. So, okay, let me first define what scattered topological spaces are. And I've been trying to locate the first paper of the textbook where this is defined, but I couldn't find it. The oldest place where I could find this definition is in a book by Kuratowski from 1948. And in it, it says that a topological space X is scattered or dispersed if every closed subset of X has an isolated point. So this is the notion of scatterness for topological spaces. And as I said, and well, as you can see, this has been around for almost 80 years at least, and it has very nice characterizations and very nice permanence properties. But well, since the talk is not really about them, I will not state them, but just know that these exist, and I will mention a couple of them in a couple of minutes. And so instead, what I'm going to be doing is just give a couple of examples of this type of spaces, and then translate this notion to the setting of system algebras. So examples, first example is the most natural example that you can come up with, which is that of discrete spaces. Since well, in here every point is isolated, and so everything is trivial. Now, by working with this definition a little bit, you can see that you can drop closeness here. And so in particular, what this implies is that the space is T0. But in general, it does not need to be T1. And just an example of that, probably the easiest example of that, is by taking a space with 2 points with the topology given by only one of the points. Just the empty set, one element, and then. So this is not T1, but it's scattered. And it's known as the Sierpinski space. And now, similar to this, if you take the integers, you can also work with them with the topology that makes this scattered. Should I have more? Okay. So with the topology generated by these triples, so 2n minus 1, 1, 2n plus 1, whatever in Z. Yeah, go ahead. Which one? A, B? Oh, no, that's me not being able to write. But yeah. So it just, so the topology, I'm just giving the open sets, or the sets that are going to be open. Yeah. Okay, so as I said, these are spaces that are well studied. And for instance, if you start adding more assumptions to it, you sort of get also nice properties. So if a space is T1 scattered, it is immediately totally disconnected. And if it's second countable and scattered, it's countable. So this is just some of these properties. And as I said, now the goal is to translate this into the setting of system algebras. And one way to do this is by noting that luckily we have locally compact Hausdorff scattered spaces. So we can just look at the commutative system algebras that have associated, well, have these spaces associated to them, and then study those in hopes that we can find the definition of scatteredness in the general setting. So this is a remark. As I said, I start with a topological space. So let X be locally compact Hausdorff scattered space. Then, in order to apply the definition, we need a closed subset. So I just take it. So take Y inside Y is closed. And now, by definition, this has an isolated point. Just take that. Y will be isolated. Now, since the point is isolated, the indicator function at this point is continuous on Y. So the indicator function, it takes value 0 everywhere except 1 on Y. So that's continuous precisely because it is isolated. So let B in C0Y be the indicator function of Y. And so we get a projection which is continuous, and it also has a very nice property, which is precisely what we are going to need to define scatterness in the system algebraic setting. What this satisfies is that then P times C0Y times P is CP. I'm fully aware that I do not need one of these P's, but I have a vested interest in writing things this way. So now, what these remarks suggest is that just like closed subsets translate to quotients in system algebras, the notion of isolated point translates to that of a projection that has this property. So now that we know the translation, or a possible translation, of closed subset and isolated point, we just can take the topological definition and change those words. And that's going to give us the definition for system algebras. So definition, as I said, the original definition is due to Jensen, but the one that I'm giving is an equivalent one by Glemm and Kosmaida. So the definition, as I said, is changing a couple of words. So a sister algebra A is scattered if every quotient H1y, where y is close to sided ideal, contains a projection such that the previous equality holds. So p times y times p. So these are scattered sister algebras. And as I said, the point of this definition, or the good thing about this definition, is that now we can translate many things that hold for scattered topological spaces. So just to give you a few results on that, but as I said, the main protagonist of this talk is not really this family of sister algebras, but rather the ones that are really far from them. First of all, let me just note that. Yeah. Right, but so for von Neumann-Chester algebras, this is exactly the same as being minimal. It's the same thing. But in general, for sister algebras, that's not true. So this always implies minimality of the projection, but the converse does not hold. If you are in the real rank zero case, that's true, but if not, that's not true. And the proof in the real rank zero case is the same as proof for sister algebras. So, okay, first a remark just to note that this definition is truly well done, is that if you take a commutative sister algebra, then this is scattered even only if its spectrum is, or even only if X is. And so one implication is just the previous remark. For the other one, you need the space to be, let's say it's completely irregular, but you have this because you are locally compact and Hausdorff. And more generally, if a sister algebra is separable, then it is scattered even only if its spectrum is scattered. This is something that one can prove. And so, as I said, the point of this definition is that now we can translate many of the characterizations that one has in topological setting. So this is a theorem by Manning. So if A is a sister algebra, then the following are equivalent. So first, A is scattered. To every element in A is A, so every self-adjoint element has countable spectrum. Now, 3, every subsystem algebra of A as real rank 0. And for every subsystem algebra of A is AF in the local sense, not assuming separability or having a unit. So this simply means that for any finite number of elements, you can find a finite dimensional subsystem algebra that approximates those elements. And so the interesting thing about this theorem is that at least the first two characterizations are truly translations of topological characterizations of scatteredness. So for instance, it is known that a space is scattered even if every real valued continuous image of the space is countable. So that's the translation of this. And it's also known that being scattered, at least in the locally compact Hausdorff setting, is the same as every subset of the space being zero dimensional, which is sort of the translation of this.
What does real rank 0 mean?
Yeah, so In the unital setting, it just means that self-adjoint invertible elements are dense in the set of self-adjoint elements. And in the non-unital, you take the unitization and look at if this happens or not.
And also, can it just another, how does these, so if you go to discrete spaces, I guess there's an analog of a C-star algebraic discrete. As in here, so these scattered spaces are generalizations of discrete spaces.
Yes.
So can we see in the definition here for in terms of projections or in one of the equivalent ones in the theorem, what discrete would reduce down to in the commutative case?
In the commutative case, it's just, I mean, just discrete spaces.
Sure,
right?
but
So
I'm saying, let's say,
right.
for example, can you see every element in the spectrum has countable, every element in the self-adjoint is countable spectrum. For the discrete, what would that reduce down to as the special case? Finite or something?
Anything? I don't think so. I will think about this, but I don't know. So
I guess the projections that you have, right? The minimal ones, but
yeah.
I guess if those generate those, maybe that would be discrete.
Oh yeah, yes, yeah, probably, yeah. That's right.
Also with A, I guess in the non-separable case, probably LF, like it's not quite. These finite signals, I guess.
Yeah, but what you say does make sense. I mean, just saying that this generates in some sense.
Well, this is great.
Yeah.
I'm just saying for this theorem. So
Oh.
it's a separate issue. But I mean, in the non-separable case, it's not quite.
Yeah. So let me just write locally.
Yeah.
Which is just truly what I meant. Yeah. Okay. Oh, let's say yes, no problem, and then it's just copies of C. Yeah, which goes back to that. Yes, exactly. So, okay, so these are scattered C-star algebras, which, as I said, what we want now to define are those C-star algebras that are really far from being like these ones. So in order to do that, just note that from the definition of scattered C-star algebras, in order for a C-star algebra to not be scattered, it is enough for one quotient to not contain such a projection. So instead, what we ask of nowhere scattered C-star algebras is for no quotient to have that kind of projections. Definition. A C-star algebra is nowhere scattered if no quotient of A, so no quotient A not Y has a projection such that P mod Y P C. Now, the idea behind this, and maybe it's a little bit naive, is that if you were to measure or grade the level of scatterness that a C-star algebra has, in one extreme you'd get scattered C-star algebras, and in the other you'd get this sort of C-star algebras, nowhere scattered. And since we know that there are permanence properties and nice characterizations in one of the extremes, you somehow expect that you are going to get nice things also in this extreme. So that's sort of the idea. And this is in detail. So theorem. And this is just a short selection of a really long list of characterizations. If A is a C-star algebra, then first, A is nowhere scattered. Secondly, A has no non-zero scattered real quotients. Well, real quotient is just the ideal of a quotient. B, which is the most useful, A has no elementary, no non-zero elementary quotients. And for in terms of reducible representations, this is the same as no hereditary subsystem algebra. No hereditary subsystem algebra. Okay. One-dimensional or equivalently finite dimensional reducible representations. Okay, so yeah, go ahead. No, what I yes, exactly. But yeah, so that's so your remark. I mean, what this implies, what you just said, is that you have no commutative system algebras that are nowhere scattered, which I was just about to mention. But there are spaces that are nowhere scattered. It's just that none of them are the spectrum of a commutative system algebra. Yeah, I will get to that in a couple of minutes.
One-dimensional reducible representations, one-dimensional ones are already reduced, right?
Well, yeah. Okay, so yeah, I didn't say that it was non-zero. So yeah, but yeah, that's a fair point. Yeah. So okay, at this point, I should mention probably two things. The first one is that starting here, everything as stated is joint work with hand steel.
There's a question in the chat.
Oh, yeah.
From Laurent. So is there difficulty when going to matrices, that is from passing from A to A tensor K or A
No.
tensor N?
No, there isn't. So this is unstable notion in the sense that the stabilizing doesn't change anything. So okay, well, the first thing is that this is joint work with hand steel, and the second thing is that nowhere scattered sister algebras have appeared implicitly in a number of papers. So what I mean by this is that, for instance, there are some papers where some results are about sister algebras that have non-zero elementary ideal quotients, or there are other papers where they talk about sister algebras such that their hereditary subsystem algebras have this property. So truly the point of this theorem is to say, well, this class of sister algebras, which has already appeared a number of times, should have a name and should be studied sort of systematically. And the name that we propose is nowhere scatterness, precisely because of all this introduction that I've done. It's the or the other way around. Everything is the same. An ideal of a quotient or the quotient of an ideal. Yes. So I mean is this. If you have this, that, and that, an ideal quotient is as it. Yeah. So okay. Now with this theorem, I can already give a number of examples of nowhere scattered sister algebras. The first is a non-example, which is what you just mentioned. So C0 of X, the commutative sister algebra, is never nowhere scattered. And the reason for this, for instance, is because all commutative sister algebras can be reducible. So in this setting, in the setting of commutative sister algebras, one can truly see that these notions are really far apart, since there are only a few commutative sister algebras that are scattered, which are precisely those that have scattered spectrum, and there are none that are nowhere scattered. So now, for the first example of nowhere scattered sister algebras, almost all simple sister algebras will be nowhere scattered. So a simple sister algebra is nowhere scattered if only if it is not elementary. This is simply because of this third condition. So if you're simple, the ideal quotient is yourself of 0. So by using that, almost every simple system algebra is nowhere scattered. And also using that third condition, one can see that all traceless system algebras are nowhere scattered. So trace, let me see if I got this correct. System algebras are nowhere scattered. And this includes purely infinite, and even more generally, weakly purely infinite system algebras. Because again, if you have a non-zero elementary ideal quotient, that elementary ideal quotient has a non-trivial trace, well, quasi-trace, and you can leave that to the whole system algebra. So traceless system algebras must be nowhere scattered. Yeah. So, well, purely infinite in the non-simple setting, I'm taking as a definition that in the Kunzing group, which I will define in 20 minutes or so, 2x is superequivalent to x. Say A0, 0, A equivalent to A0, 0, A. System algebra. And weakly purely infinite, what it means is that you must have some sort of n. So at the level of the Kunzing group, I will get back to this once I define this. But so purely infinite in the level of Kunzing groups is that this happens for every element in the Kunzing group. And weakly purely infinite is that this must happen for some n. And it's an open problem if these two things are the same. And this is actually related to the global Gleam problem. So is this the thing that I have to use to? Okay, so I can try this one, and well, let me just use this and see if it works. Okay.
And so,
yeah.
What's an example of a scattered C-star algebra that's not a billion? I mean,
Well, the 2 by 2 matrix over C.
that's the infinite dimensional non-abelian.
Yeah, I mean.
No, I mean infinite dimensional.
Yeah. The compact operators.
Compact operators.
Yeah.
Would do. So
Yeah.
Okay, yeah, that would do. So, but it has to be something, I guess, elementary. Is that a fact?
Yes, that's point. So
Nice.
yeah, and that's why in the nowhere scattered case, you sort of get that elementary.
Right.
No, it doesn't. But like the natural examples are of elementary things.
Or extensions by elementary guys, right? So you can get
Yes.
this sort of tower of ideals.
Yeah, exactly.
Okay.
Yeah. So how am I doing it? Okay. So okay. Well, I can skip a couple of things. Now let me just mention that, as I said when I was defining nowhere scatterness, one does get really nice permanence properties. But because I don't really have the time, I will just say them out loud, and that's it. So nowhere scatterness passes to hereditary subsystem algebra, so in particular ideals. It also passes to quotients, it passes to inductive limits and to approximations, so it works fairly well. And also system algebra is nowhere scattered, if only if an ideal and the corresponding quotient are nowhere scattered, which is also a property that scatterness has. The only things, or maybe the most notable things that do not work well with nowhere scatterness are minimal unitizations, which always fail, because if you are not unital, A tilde mod A is C, which is elementary. And also the multiplier algebras don't really work well. In some cases they do, so it's not as bad as the minimal unitization, but in some cases they do not. So I don't know what. Okay, So now let me just finish this first section on nowhere scatteredness by saying that, like in the scattered case, nowhere scatteredness is characterized by the spectrum of the system algebra in the separable case. So first of all, one has to define what nowhere scatteredness means in the topological setting, but this is just doing what I've just done in the introduction, but sort of the other way around. So now topological space X is nowhere scattered. If no closed subset of X has an isolated point, and this just works. So it turns out that in a separable setting, separable system algebra A is nowhere scattered. If only if the spectrum of A is nowhere scattered in this case. Yeah.
Question. Every subsystem algebra of A has real rank 0 implies nowheres. I mean, scattered. Yeah.
Yeah, it's the same thing.
And then, but purely infinite, guys. they're
That's
real
nowhere.
rank 0.
Yeah, you can have real rank 0.
Just not every subset.
Exactly. So, for instance, I mean, if you take the continuous functions over the Cantor set, that has real rank 0 because the dimension is 0, but C of 0, 1 embeds. So C of the Cantor set is not scattered. And also, yeah. So, okay, this is the last thing that I wanted to mention about nowhere scattered system algebras. And now I will talk about the global Gleam problem. So I've very purposely not stated two characterizations of nowhere scatteredness because they are deeply related with this global Gleam problem and the global Gleam property. So to start the section, I will give one of these. Go ahead.
I want to ask you a question. So if you have a number a scattered system algebra and then you cross product by kind of actions, can you get the number scatterness?
Yes,
Again,
but
or-
only in some cases. So I was planning to get away without saying anything. But so the only thing that we know, which is, I mean, so we do not state anything for cross products or anything like that. But it is true that if you have A nowhere scattered, and remember this, but if you have a G, a countable exact group, acting on A, and such that the induced action in the spectrum is essentially free, then you do get that the cross product is nowhere scattered. So, well, all these imply that cross product. Yeah. But this is, I mean, this is not something that we state as a result, because this follows as an example of something else. Mainly that if you have a subsystem algebra which separates ideals, so that means that ideals can be distinguished in the subsystem algebra, then if that subsystem algebra is nowhere scattered, the whole system algebra is also. And so really what we're using here is a result by someone who I don't remember the name, which states that in this sort of setting, A as a subsystem algebra will separate ideals. So that's the only thing that we know when it comes to cross products. Okay, no problem. So, okay. Now, as I said, there are two characterizations that I didn't state. One of them is the one that I'm about to state. So this is the second section, which is the global Gleam problem. And so we'll begin the section with this characterization, which I'm writing as a remark, but it probably should be a lemma or a proposition, something like that. So a system algebra is nowhere scattered. I have to change this. The condition that I'm about to write holds. So if only if for every positive element A, every integer greater or equal than 2, and every positive epsilon, you can find morphisms finally many of them. So let's say phi 1 up to phi n go from C0 or 0, 1 tensor mk this hereditary subsystem algebra. That's that A minus epsilon positive is the ideal generated by combined images of phi 1. So, okay, this is a characterization of nowhere scatterness, and by looking at it, one can note that you have control over almost everything. So what I mean by this is that this size of these matrices is something that you chose, which is this K. This hereditary subsystem algebra is also chosen, which is this A here, and this retraction is also chosen because you've chosen the epsilon. So the only thing that you cannot control a priori from this definition is the number of maps that you get here, the number of stack homomorphisms. So a natural question to ask is if you can actually control them, and even more natural is to ask if you only need one stack homomorphism. And if you do, if you only need one stack homomorphism for any selection of these things, the system algebra is said to have the global Gleam property. So this is the last one that I did. So, oops. A, which is this system algebra, has global Gleam property. If one can always do this, and by this I mean that thing with equals 1. And this is so now, because of this remark that I've just given, it's clear that every system algebra with the global Gleam property will be nowhere scattered. And so what the global Gleam problem asks is if the other direction also works. So if every nowhere scattered system algebra has the global Gleam property. Problem. This is the global Gleam problem. Is it asks, does every nowhere scattered system algebra have the global Gleam property? So this has been answered affirmatively in a number of cases, but in general, the problem remains open. In particular, what one can show is that purely infinite sister algebras in the non-simple setting have this property, and weakly purely infinite have the other property, nowhere scattered, as I said. So a particular, let's say, implication of answering this affirmatively is that every weakly purely infinite sister algebra is purely infinite, which again, that's also open. So that's the problem. And in sort of similar problems, an idea that has a lot, or at least that seems to be working, is to use the Kunz group to approach this. So the idea of this problem is use the Kunz group.
A weakly purely infinite C-star algebra, and you could somehow show that it has the global Gleam property, then it actually has to be purely infinite.
Yes, and this is in this paper.
Okay. Cool.
So now, since I will state some things with the Kunz group, I will first define it. So I will be very quick on doing so, because I know that Laurent Canty is going to give you a lecture or a couple of lectures on the Kunz group. So I will just list a couple of things and leave the details to him. Mainly, the Kunz group, as the name indicates, is an invariant introduced by Kunz, which attempts to generalize the Murray von Neumann semigroup of projections. And the idea there is to use positive elements instead of projections. So Kunz group as I said, the point is to use positive elements. And the reason for this is because there are many sister algebras that either have very few projections, or even if they do have a lot, then the Murray von Neumann semigroup might not tell you much. But in every sister algebra, you always have an abundance of positive elements. So the idea is, if I can sort of manage to create this Murray von Neumann semigroup for positive elements, it will always tell me something about the sister algebra. So that's the idea behind it. And now the definition of the Kunz group is just copying, in some sense, the Murray von Neumann construction, but changing everything so that everything works with positive elements. So just like in the Murray von Neumann case, we start with two elements, which now are two positive elements. And we define equivalence and unequivalence. So we say that A is Kunz equivalent to B if A is the limit on n of Rn B Rn star some Rn. This attempts to generalize the Murray von Neumann superequivalence. If you have two projections, this is actually the same thing. So now 2 A is equivalent to B if A is equivalent to B and B is equivalent to B. Now, our sort of a warning in the non-residually stably finite setting, this is not the same as the Murray von Neumann equivalence, but in that setting it is. So now that we have a superequivalence and non-equivalence, we can just copy the definition of the Murray von Neumann semigroup. So definition, the Kunz group of the sister algebra is, first of all, it's denoted by C of A. And once again, we just do the same thing as in the Murray von Neumann semigroup. So we stabilize our sister algebra, and instead of taking projections, we take positive elements and we quotient them out. And now, when one talks about the Kunz group, one usually refers to this with a particular addition and order. And so the Kunz group is not just this, but it's this equipped with the addition of first the order induced by that superequivalence and the addition induced by diagonal addition. So by this induced here, I simply mean that the class of an element A is going to be less than or equal to the class of an element B, if only if A is supercurrent to be in A tensor B. So that's the Kuhn semigroup. And in the Kuhn semigroup, when usually, other than the order and the addition, uses something that's called an auxiliary relation, which is very useful to define notions on this monoid. So something that I forgot, the Kuhn semigroup with that order and that addition becomes a positively ordered monoid. So, okay, this auxiliary relation is called the way below the compact containment relation. And this is just that A is compactly contained in B, where A and B are elements in the stabilization. If A is supercurrent to B minus epsilon positive for some positive epsilon. So this is not the original definition, but one can check that it is equivalent to this. So, okay, now with this relation on the Kuhn semigroup, I can define divisibility conditions on the Kuhn semigroup. In particular, I will need two of them, which as I write them, I'm sure that you'll see precisely why I need them. So the definition, this is Robert and Rordan. I have to look, I think it's 2008, but I should check. No, 2013. So there are two divisibility conditions, one which is stronger than the other one. First, C of A, the Kuhn semigroup of a system algebra is weakly 2 omega divisible if whenever you have a pair x prime way below x, which again, this is just this notation. So x prime is the class of an element A, x is the class of an element B, which satisfy that property. So whenever you have this, there exists finite number of elements in C of A such that x prime is less than the sum and 2 times yj is less than x for every j. And now the same question that we did before can be stated in here. So can we make do with taking all the y's to be the same one? And if you can, this is known as 2 omega divisibility. So 2 C of A is 2 omega divisible if whenever you are in the same setting, whenever x prime is way below x, there exists only one element, so exists y in S and some natural number and such that x prime is less than or equal than y and 2 times y is less than or equal than x. So now looking at this definition, you probably expect what comes next, which is that one of these is equivalent to nowhere scatterness and the other one is equivalent to the global Gleam property. So, oh, I'm sorry. Yeah. Yeah. So, okay. I do have examples of these things, but I don't have the time to write them all. In any case, if someone wants the examples, you can ask me later. So now theorem, and this is the part that is sort of ongoing. Not this first theorem, but the second one. Theorem C of A is weakly 2 omega divisible even with the system algebra is nowhere scattered. Now this goes back to a question that I had in the beginning. Because the Kuhn semigroup characterizes nowhere scatteredness, this implies in particular that going to matrices doesn't affect this. Because the construction of the Kuhn semigroup stabilizes. So second theorem, which is the part of the ongoing part. So C of A is 2 omega divisible even if A has the global Gleam property. So in other words, the global Gleam problem can be translated purely by asking something that's in some sense algebraic. So by asking if every weakly 2 omega divisible Kuhn semigroup is 2 omega divisible. Now, this is also part of upcoming work. Theorem. There is one condition which is satisfied by many system algebras that actually does give you this equivalence. So in the residually finite case, which we don't think it's needed, but right now, because of the details, we have to add this. So if A is residually stably finite, then the following are equivalent. One, A has global Gleam property, which is the same as being 2 omega divisible, and 2 is nowhere scattered and C of A is ideal filter, which is a notion that not defined, but this is something that is satisfied by many system algebras. For instance, every real rank 0 or stable rank 1 system algebra has ideal filter concept. So now, assuming that this can be dropped, which presumably it can, the global Gleam problem is reduced to proving that every nowhere scattered system algebra has ideal filter concept, which is presumably far easier, because again, this is a property that is satisfied by many systems. So in particular, what I mean by this is that there are real rank 0 or stable rank 1 system algebras that are not nowhere scattered, and they still satisfy this. So this recovers known results. For instance, stable rank 1 and real rank 0, which were positive answers that were known, are recovered because of this. So that's all I wanted to say. Thank you.
Any question or comments?
Can you just repeat what you just said? So
Yeah.
if the algebra is either real rank 0 or stable rank 1, then it has this ideal
It has this
filter.
property. Yeah.
I see.
So in the real rank 0 case was already known in the global Gleam problem. So I mean, what was known is that if A has real rank 0, then these two things without this are equivalent. Now, so the point is that there are real rank 0 system algebras, for any elementary system algebra, for instance, that is not nowhere scattered, but they still have this property. So that's sort of the idea behind this. And the same goes for the stable rank 1 system algebra.
And stupid question. Can you remind me what residually stably finite?
Oh yeah. So stably finite just means that projections are finite. I mean, the projections in the stabilization are finite, and residual stably finite means that in each quotient this still holds.
Right. And another stupid question. Can you remind? So this is the global Glimm problem, but there's also the Glimm halving.
Yes,
problem?
which is that's local. That's what. So this is the global. The Gleam halving property and the Gleam halving problem is where these definitions come. So these definitions are given by Robert and Gordon, but they are not truly these definitions. They only apply this to a fixed x. So they say an element x in the Bunsen group is weakly 2 omega divisible or 2 omega divisible if this happens. So that's purely local. It's something that's asking something local. Instead, in this setting, since we're asking every element to satisfy this property, so that's the same as saying that every element in C of A is weakly 2 omega divisible or 2 omega divisible, you actually have huge reductions. So as an example to this, so if, for instance, take A to be the 2x2 matrices over C, for example. Now, the Bunsen group of that, so C of A, are the natural numbers isomorphic with the usual order addition. And this is just seen by taking the rank function of the operators. So now in this Bunsen group, you can take X to be the class of the identity in A. And this is identified. And I don't know how to write this. Let's just say this with 2. Now, 2 in here is a 2 omega divisible element. But this Bunsen group is not 2 omega divisible. Because, for instance, if you take, I don't know, y, which is 1, 0, 0, 0, this is 1, you cannot possibly find something that's 2 times below 1, except if it's 0. But then you look at this property, and you somehow have to have that 1 is also below sometimes. Yeah. So there is truly a difference between these two notions, like the local notion and the global notion. And in particular, what the global notion implies, which is not true in the local case, is that 2 omega divisibility in the whole Kuhn semigroup implies 3 omega divisibility and 4 omega divisibility and so on. So that these two can be changed to a 3 and 4 or 5 and so on, simply by induction. But if you only assume this for an element, you cannot do that. And this is, I mean, this is strongly used. The fact that you can put a 3 or a 4 here is strongly used in the theorem that I just mentioned.
I have another question. In this setting, that number scattered of the cross product. So in most setting, I mean, the interesting case is when the action is outer, and when the action is outer under some assumption perhaps on your group, so you came up with cross product is simple.
Yeah, then
and you
that's
already have a kind
unless
of
it's elementary.
Yeah,
unless it's elementary, but truly you do not want those sort of cross products. So,
yeah.
For all intents and purposes, all simple cross products are never scattered.
Yeah, because I was thinking putting some additional things like dropping property of water.
Yeah, but that will make it. Yeah. Exactly. Yeah.
Okay. Any other comments?
Yes. Well, I said it, but I never wrote it. But yeah. So quotients, ideals, and everything sort of works well. But I mean, it's even stronger. So you have that A is nowhere scattered. Nowhere scattered. Even with the quotient and the ideal. So it's, I mean, it works with quotient, but it even works better than you might expect. This thing, oh, direct sums? Or, yeah, direct sums work. Yeah. Yeah, so inductive limits work. Sums also work, but products do not. And this is sort of the point of the multiplier algebra. So, I mean, with this example, I have no idea what this is from, but then you have a family of system algebras, I think that even countable, which are simple but not elementary and non-zero. Let's just say non-elementary, such that somehow when you take the product, this has a one-dimensional irreducible representation. This is an example by someone, which is, I mean, it's cited in the paper. So in particular, what this means is that all these are simple and non-elementary, so they are nowhere scattered. The sum is also nowhere scattered because the sum works well. But when you take the multiplier algebra, then this is just the product. It's not nowhere scattered.
Is there a way to have a very large universe in some sense?
Yeah, I think I'm fairly certain that there is a maximal ideal that is nowhere scattered in every system algebra. I don't know if that's the question. Yeah, but it can be zero. Yeah. Well, yeah. Yeah,
But like, so from your results that you've proved, or do you actually think that it's correct that the two are equivalent?
this, I mean,
Can
one
you
thing that
remove the
well,
condition?
the one thing that we are almost certain is that this,
Yeah.
I mean, it's a conjecture, let's say. So
Sure.
this is a question.
Yeah,
It's not a
but in your,
conjecture.
that's, I guess.
I would like to think that it can,
Yeah.
but I don't know.
You don't know. Yeah.
I throw it out.
But like after proving this result, are you more sure that it's true or less?
I have no
You
idea.
don't need to
I mean,
answer that
this
question.
I mean, this is truly my opinion. I really don't know. Like what I can say is that my feeling, especially going over the proof a number of times, is that this should be, one should be able to drop this. But maybe it's way harder than I think. So it might be the case that we publish this on the archive and it's still defined, and then at some point in the future. Drop it.
Any final quick question or comment from online participant?
Oh, there might be some.
Okay, there is no comment. Okay. If not, let's thank Eduard again. Thank you so much. And for next week, the speaker, we have someone. Okay, Karen can introduce.
Next week